Okay,
Can I start?
welcome everybody. Thank you very, very much for joining us once again at our weekly astrophysics seminar here at the Institute of Astrophysics. Today, we're very happy to have with us Dr. Bia Boccardi from the Max Planck Institute for Radio Astronomy in Bonn. Dr. Boccardi studied at the University of Bologna, where she obtained her bachelor's degree in physics and her master's degree in astrophysics and cosmology. And in 2012, she moved to Germany and she became a PhD candidate at MPIfR in Bonn, where she obtained her PhD. And in the past 5 years, she worked there as a postdoc in the VLBI department and as a visiting postdoc at INAF Bologna and the University of Valencia. Since August 2020, she is a junior research group leader at MPIfR. And today she will talk to us about a high-resolution view of the faint cores in nearby radio galaxies. So without any further ado, Bia, the floor is yours.
Thank you very much for the introduction and for inviting me. So I'm gonna, do you see my full screen?
Yes.
Good. Okay, good. So today I will present some of the work we have been doing in our group for studying the formation of relativistic jets through high resolution observations and focusing mostly on nearby radio galaxies. So as I think there may be in the audience some people who is not completely familiar with the topic, I will first introduce some of the basic concepts which are required. And then I will continue with more specifics of the work. So first of all, my research focuses on active galactic nuclei. As you know, all galaxies harbor a supermassive black hole at their center with mass of about 10 to the 6, 10 to the 10 solar masses. But a percentage of galaxies is special, we call them active, because they harbor at the center an active galactic nucleus. This means that the black hole is accreting material from the surroundings, and in this process, a very big amount of energy is released, so that the nuclear regions can become much brighter than the entire stellar content of the host galaxy. Here to the right, you can see a sketch of a classical picture of an AGN. Let me tell you already that this picture does not really apply to all active galaxies. It applies especially to the brightest objects which we know, in which the gas and the dust feeding the nucleus are stored in the form of a thick torus, which can obscure the nucleus depending on the orientation with respect to the observer. We also have some other gas clouds which produce broad emission lines or narrow emission lines. And in a minority of active galaxies, we also observe a pair of relativistic jets. And we call these active galaxies traditionally radio loud because these jets are particularly prominent in the radio band. In my talk, however, I will also deal with lower luminosity objects, which we can now study much better because our instruments are becoming more and more sensitive, in which, for instance, we believe now that the torus is not present and there is not really a disk in the traditional sense, but there is rather a hot accretion flow. So it doesn't let me change slide. Okay, here it is. Let me tell you a bit more about relativistic jets. These jets are really spectacular objects because they propagate in being very, very collimated up to very large distance from the black hole, sometimes even megaparsec. And they emit across the entire electromagnetic spectrum, mainly through synchronous and inverse Compton processes. Although, as I said, they have been best studied in the radio band because it's the band where they are more prominent. And here you can see an image of MIT-7, which is one of the most famous nearby jets, where both the X-ray emission and the radio emission are shown. So since jets transport huge amounts of energies from the black hole outwards, far beyond the host galaxy, they are very, very important in the evolution of the large-scale structures. This is what we call feedback. However, while playing such a pivotal role in the history of the universe, we still don't understand some fundamental things about them. Mainly, we don't understand how they are formed, and we don't understand why only a minority of active galaxies form jets. Um, the reason why answering this question is so difficult is first because the physics in the surroundings of black holes is very, very complex. To describe the processes in the vicinity of a black hole, we require the treatment of general relativistic magnetohydrodynamics. And of course, this is difficult, and great progress has been achieved lately through the use of simulations. From the observational point of view, it is difficult to answer this question because even though jets propagate for such long distances, the fundamental processes that contribute to the formation of jets happen on very, very small scales, typically smaller than 1 parsec. And such scales are too small for most telescopes. Um, the best technique, actually the only technique which can allow us to obtain a direct imaging of the fundamental scales where the jet form and initially propagate is very long baseline interferometry. This is a technique used in the radio where basically we use a large number of telescopes spread all across the Earth that observe at the same time the source, and then we combine this signal to in the end obtain a resolution which is the same as the one which we would obtain with a telescope which is as large as the Earth, or at least as large as the maximum separation between two telescopes. And here you can see that the resolution depends on the wavelength over the d, which is the maximum separation. Traditionally, in the past decades, VLBI arrays have mostly operated in the centimeter regime, so at frequencies between 1 and 22 gigahertz, which allow us to reach resolutions of the order of the milliarc seconds, and therefore to probe mostly jets on parsec scales. So what do we see when we observe an Aegean jet with very long baseline interferometry? We see something like this. We see a bright core and a one-sided jet. The core is characterized by a very high brightness temperature, especially during flaring events, and its nature is still debated. It may be a first strong shock at the base of the jet, or it may mark the transition between regions optically, between synchron emitting regions which are optically thick and then become optically thin. In the latter case, we expect the core position to be not fixed, but to be dependent on the frequency. And therefore, by going at higher frequencies, we expect the core to move closer and closer to the black hole. This is what we call the core shift effect. We also observe a jet, which, although it may appear somehow a little chubby, in reality, this is just because of projection effects. In reality, is a very narrow channel, which typically has a conical shape with an opening angle of the order of only 1 degree or even less, which is crossed by fast-moving shocks, which have a Lorentz factor of the order of 5, 10. Here you can see the expression of the Lorentz factor, where beta is the intrinsic speed in units of speed of light. So why do we observe only one jet when intrinsically we know that there should be two symmetrical? Is the one-sidedness, this is how we call it, is a selection effect which is due to the relativistic nature of the flow. Indeed, when a flow moves with relativistic speed, its emission can be strongly amplified by a factor of delta to the 3 minus alpha, where alpha is the spectral index, And so this D is the Doppler factor, which depends on the intrinsic speed, but also on the viewing angle of the source. So if a source it points directly towards us, so if it forms a small angle theta with respect to our line of sight, we're going to have a large Doppler factor, and therefore the emission is going to be much stronger than intrinsically. And this is the reason why in VLBI surveys especially, we mostly detect blazars, which are objects with jets pointing at an angle, let's say less than 10 degrees with respect to our line of sight. So these blazars come in two different flavors mainly. We have a low power population, which is formed by BLX, which we believe are these low luminosity objects, which I was mentioning at the beginning, which are powered by hot accretion flows, and we also call them low excitation objects because they don't produce strong emission, broad emission lines. And we have the high power population of the flat spectrum radio quasars, which instead we believe are powered by more classic disks, classic cold disks, and we call them high excitation objects. Now, when we observe blazars at so there is a parent population of blazars that instead is formed by the jets, which are pointing at a larger angle with respect to the line of sight, and these are the radio galaxies. The radio galaxies are classified historically based on their morphology as Fanaroff-Rayleigh 1 and Fanaroff-Rayleigh 2. The Fanaroff-Rayleigh 1, they are characterized by a stronger brightness in the nuclear regions and by the rapid fading of this emission on larger scales. And they're also less well collimated objects. While the FR2s present jets which are very well collimated up to large distances and form bright hotspots at the end of their path where they dissipate their very large kinetic energy. And overall, although there is not a one-to-one correspondence, we believe that BLX are the parent population of FR1s, while FSRQs are the parent population of FR2s. So this is in a simplified scenario. Of course, there are exceptions. For instance, there are several sources with FR2 morphology that instead harbor low excitation nuclei. I will come back to this also later. So what are the advantages and disadvantages of studying radio galaxies with VLBI? The main advantage, especially if we aim at studying the formation of jets, is that we can much more easily infer the intrinsic properties of in radio galaxies with respect to blazars. This is because the Doppler factor is much reduced, therefore we can observe we can observe actually the source in close to its intrinsic properties, and also projection effects are much reduced. So the real physical scales which we can probe are actually much smaller. The disadvantage, of course, is that because the Doppler factor is smaller, of course, these objects are generally faint. One thing I want to mention about the Doppler factor, which is something that is not sometimes not remembered, is that if the viewing angle is large, and if the intrinsic speed is also large, we can have a deboosting of the emission, so a Doppler factor smaller than 1, even in the approaching jet in radio galaxies. So this is a concept that will be useful for something that I will mention later. So let's say something more about what we know about jet formation. We believe that the formation of jets is driven by the presence of very strong magnetic fields which are accumulated in the innermost regions of the accretion disk. And these strong magnetic fields channel the jet, and by extracting the rotational energy of the accretion disk in a process which was originally described by Blanford and Payne, or also they extract the rotational energy of the black hole if this is spinning. So we may have a process in which the accretion disk contributes to the formation of a collimated wind, while the black hole produces a jet which is maybe lighter and faster at the center. So at the beginning, these jets are we expect them to be slow, very broad, and strongly magnetized. As the acceleration of the flow proceeds, and also the collimation, because the acceleration and collimation are thought to occur at the same time in this scenario, the magnetic energy which was dominating at the base of the jet is gradually converted into kinetic energy as the backflow becomes faster and faster. And this process, in the description of this process, the fundamental scales that describe the extent over which the acceleration and collimation occur is the Schwarzschild radius. So the extent of this acceleration and collimation region is expected to be dependent on the mass of the black hole. So this is the expression for the Schwarzschild radius. So the larger the black hole mass, the larger will be the Schwarzschild radius. However, from what we know from observations of blazars with VLBI, we think that usually we probe in VLBI observations the region where this acceleration and collimation has already occurred. So we need to go deeper we need to penetrate deeper the jet base in order to be able to probe this region. So remember what I said before about the nature of the core. If the core actually is the location where the jet is becoming, the emission is becoming optically thin, then we can penetrate closer and closer into the jet base by observing at higher and higher frequency. So we need to observe in the millimeter regime. So far, we have mostly observed in the centimeter band, and we need to move at shorter wavelengths or higher frequency. As you remember, going at higher frequencies also mean that we increase the resolution of the interferometer because the wavelength gets smaller. So through observations through millimeter VLBI observations, we can attempt to probe unexplored regions in the vicinity of the black hole, and in particular, nearby radio galaxies with large black hole masses are ideal targets for such a study, because the Schwarzschild radius is large. Therefore, we can obtain a high spatial resolution in units of Schwarzschild radii. Let me give you a small overview, a short overview, which millimeter VLBI arrays do we have today. You certainly know the Event Horizon Telescope, which has most recently produced the first image of a black hole. This is an array which observe at really high frequency in the sub-millimeter band, or 230 gigahertz, 345 gigahertz. But at the lower frequencies, we have a number of other arrays. From the very long baseline array, we have global VLBI arrays where we have stations really across on the many different continents. We have the high sensitivity array where we put together the most sensitive telescopes to reach really high dynamic range images. We have the global millimeter VLBI array, which observes up to 3 millimeters and also includes the ALMA telescope. So let me tell you a bit more about what do we know concerning the jet base that we have learned so far from millimeter VLBI observations. As I said, we believe there is a region at the base of the jet where the magnetic energy is dominant. The jet is accelerating and collimating there. And typically in blazars, the millimeter core is located at the end of this region. So we have the launching region where the jet is still very wide and slow, then gradually it accelerates and collimates, and we think that this occurs on a scale of about 10 to the 5 Schwarzschild radii, after which basically we have a jet which is dominated by the kinetic energy of the bulk flow, and this is the region where we start observing shocks and instabilities. And finally, on very large scales, this kinetic energy is dissipated in the forms of diffuse emission. So, but as I said, this picture is largely based on what we know based on the study of very few objects, mainly M87 and few other bright radio galaxies. So we need to it would be the aim of this talk of this work is to expand the sample of sources which we can use to test this scenario and better constrain the regions where these processes occur. So let me mention some very short highlights on what it has been done so far, and so how we build this picture which I have described. Here I'm showing millimeter-VLBI observations of some nearby radio galaxies. Here you can see the FR2 radio galaxy Cygnus A, then there is M87, which is a low power FR1, and then there is 3C84, which is also an FR1, but atypical, let's say, not a classical FR1. A common feature of these jets is what we call limb brightening. So when we are actually able to resolve transversely the jet, we see that these flows are not really uniform, but they are strongly stratified, and the emission is typically brighter at the edges of the jet. This may be a signature for the existence of a velocity gradient in the jet. This is what I was mentioning before. If there is a fast spine at the center of the jet, then due to the fact that we are observing these jets at relatively large viewing angles, then the Doppler factor of the central part of the jet will be lower than the one at the edges of the jet, which probably moves slower. And this may result from the fact that these Blanford-Payne and Blanford-Snayak processes are happening at the same time. So we have slow outer sheets, which is probably also heavier because it is loaded with also with protons. And then at the center, we have a lighter and faster spine, which reaches the really high Lorentz factors, which I mentioned before. These observations were also able to resolve the base of the jet in order that we could really measure how wide is the apex of the jet. And interestingly, in M87, observations tell us that the jet base is really, really narrow. So we have a jet apex which is only few Schwarzschild radii wide, while in Cygnus A and in 3C84, we observe something different. We observe a wider jet base of the order of 200 Schwarzschild radii in both cases, which may point towards a more prominent component, which is driven by the disk. I will also expand more on this later. We also have been able to directly probe the acceleration of the jet. For instance, you can see here a study of M87 by Mertens et al., where we see that the flow moves along mainly three filaments with two different speeds components, one that is faster with a Lorentz factor of about 2.5 and one which is mildly relativistic. In any case, as you see, the Lorentz factors in radio galaxies are always much smaller than what we measure in blazars. And this may be, again, another evidence for what I was saying before, that in radio galaxies, we mostly see the emission from the slower parts of the jet because of differential Doppler boosting. This study of M87 enabled us to see that the speeds increase indeed in the innermost regions. They increase faster in the innermost 10 to the 3 Schwarzschild radii, and then there is a saturation regime up to about 10 to the 5 Schwarzschild radii, where the maximum speed is achieved. And similar results were obtained also for Cygnus A from the point of view of the jet acceleration. We have also studied the jet collimation. Again, here I'm showing the example of MPIfR, which is the best studied source. As I said at the beginning, we expect the jet to be accelerating in the region where it is also collimated. So the acceleration and collimation region should be co-spatial. And what you see here is basically is the jet expansion profile. So you see the jet radius as a function of distance from the jet base in units of Shashi radii. And what it has been observed is that indeed, at the beginning, the jet has a parabolic shape. So it means the opening angle of the jet is not constant, but it is decreasing continuously as the jet propagates. And this is exactly the shape that most of the models predict for in the collimation region. But then there is a transition in the jet shape where with the jet becoming conical. So this is the shape that we observe commonly in blazars, as I mentioned at the beginning. And this transition seems to occur at a distance, again, of the order of 10 to the 5 Shashi radii, which is comparable to the Bondi radius. So MAT7 is a low luminosity object, which is fed by a hot accretion flow. And the Bondi radius is simply the radius within which the gravitational influence of the black hole dominates over the thermal motion of the gas in the accretion flow. So we may expect to have to observe a discontinuity in the pressure profile of the gas inside when we go from inside the Bondi radius to outside, and this discontinuity may reflect on the expansion profile of the jet, which then, when exiting this sphere of influence of the black hole, doesn't have any more the confinement from the hot gas and therefore starts expanding freely. This scenario was proposed by Asad and Nakamura, but basically it has been studied only for one source very well. So we don't know if this is actually the case for other sources and if this is correct. In any case, especially in the past couple of years, this parabolic expansion has been observed in several other radio galaxies, and therefore we now have more elements to actually discriminate between different scenarios. So the main question is the jet actually confined by the ambient medium? Which is this ambient medium? Or is maybe the ambient medium not important at all for the jet collimation, and maybe it's only the magnetic field which collimates the jet? We still don't know. And the rest of the talk will be especially focused on this topic, which I'm in the work which I'm presenting today. So we need to expand the sample of sources in which we can test these models. How do we do that? We can either observe the very bright objects at higher frequency and or angular resolution. For instance, we can do that with the Event Horizon Telescope, but there are not really many objects which are bright enough for that. So in another approach, we can try to zoom for the first time into the cores into the faint cores on nearby radio galaxies by using very sensitive arrays, for instance, the high sensitivity array. The advantage of the second approach is that, of course, since these faint objects are in general also much closer to us, we can much better probe the environment and the accretion flow and its relation to the properties of the jet base, which is difficult to do, for instance, in the case of more distant blazars. So we have performed a first exploratory step to see if we can actually detect some of these faint cores at very high angular resolution. So we have obtained the first observations with the high sensitivity array at 22 gigahertz and 43 gigahertz for a sample of 16 radio galaxies, which are nearby at redshift less than 0.5. They host very massive black holes, and they have jets oriented at a large viewing angle. These three criteria ensure that we can actually image the jet on scales which are small enough to see the properties of the jet in this region, so on scales typically smaller than 10 to the 5 Schwarzschild radii. We also have selected them in a way that we can span different luminosity classes. So we have included 7 FR1s, 6 FR2s, and 3 objects which do not develop any structure on kiloparsec scales. We are working on this. I'm showing you here first views of the subparsec scale structures of these faint cores. We have completed the analysis at 22 gigahertz, and we are now working on the 43 gigahertz data. And the good news is that we have detected all objects, and actually these objects are brighter than we thought. Here you can see the distribution of the flux density in the K band. These sources also have brightness temperatures which are typically much lower than we observe in blazars, below the equipartition value. So there is a hint that we are actually observing the jet in a region where the physical conditions are very different from those that we observe in blazars. And the positive aspects also of these sources is that many of them show two-sided jet morphologies on subparsec scale. And this is very important in order to test the symmetry of the jet formation process in the two sides, in the approaching and in the receding side. Now, as you see in this plot, there is one source which is quite brighter than the others. And for this source, we have also requested observations at 86 gigahertz, so with the GMVA array. And in the following part of the talk, I will focus a little bit more on this source, which we have already studied in detail. And therefore, at the end, I will also compare the results we have obtained with those obtained in the literature for other sources. So the brightest source in our sample is the giant radio galaxy NGC315. This is an FR1, which is like M87, is powered by a hot accretion flow. And not only it is the brightest, it is also the best resolved source in the sample. This is due to the fact that the source is quite nearby. It hosts a very massive black hole. The most recent estimate gives a mass of about 2 billion solar masses. The angle is of the order of 38 degrees, and its size is really huge. The radio structure extends for more than 1 megaparsec. So we have analyzed a large data set, including the HSA data at both frequencies and the GMVA observation, and additional VLBI data in a broad frequency range. And here you see what we have obtained you see a multi-scale view of this source. So going from the megaparsec scale structure, which is probed by VLA data at low frequencies, and then the VLBI structure at increasingly high frequency from 5 gigahertz to 86 gigahertz. Here I'm only showing a little subset of our data set, which actually includes 18 images. And at 86 gigahertz, basically, we were able to image this source on a scale down to 60 microarc seconds, which corresponds to about 10 to the 2 Schwarzschild radii. So this is at present the second best result source after M87. It shows a faint counterjet at all frequencies, and also some hints of a brightening, which they cannot be really seen in these images, but because typically we are not able to really recover the full cross-section in a single epoch, but a detailed analysis shows that there may be a rim brightening like in the previous sources which I showed. So the main aim of this work was to determine the extent of the jet collimation region and test this scenario, which was proposed for M87, that in which the jet is collimated by the accretion flow. This work was recently accepted in ANA. So I will now describe briefly how this analysis was performed. So in order to determine the jet width at different locations, we have modeled the data by fitting a series of circular Gaussian components to the visibilities. Here you can see an example from the 22 gigahertz image. So basically, we assume the jet width to correspond to the full width at half maximum of this Gaussian. And then to reconstruct the expansion profile by considering different frequencies, it was necessary to correct for the core shift effect, which I mentioned before. So in each image, we're going to have a core which is at the 0 in our image, but physically these cores are not at the same location. So we need to correctly align the images after correcting for this opacity shift. And we've done that by performing a 2D cross-correlation analysis considering different pairs of frequencies. And here you can see what is the dependence of the core position as a function of frequency. Here I'm showing the expansion profile which we obtained by considering the entire VLBI data set. So what you see here is this full width at half maximum, which we obtained by the fitting of discussion components as a function of the projected distance from the jet base in units of both parsecs and Schwarzschild radii. And the different frequencies are labeled with a different color. So as in MPIfR, we do observe a transition between a parabolic shape and a conical shape. The innermost data points, so basically the data points at the highest frequencies, describe an expansion profile which is flatter with a shape which is close to a parabolic shape. But then already on the scales of 1 or few parsecs, we observe a shape which is which approaches the one of a cone. So a perfect cone would have here this index equal to 1, and we have 0.84. So there is a shape transition, and this shape transition occurs at a distance which is smaller than 1 parsec. So we determine a transition distance of the order of 0.6 parsecs, or corresponding to about 5 times 10 to the 3 Schwarzschild radii. So to test this scenario in which the jet is confined by the accretion flow, we have determined what is the Bondi radius in this source. And we have done this by considering X-ray data. Here you can see a Chandra image of the source. The jet actually shines in X-rays, so we don't only see a nucleus, but also an X-ray jet. And therefore, we have assumed the temperature of the hot gas in the surroundings of the nuclear region to determine the extent of the Bondi radius, which is of the order of 92 parsecs. So the Bondi radius is really much, much larger than the distance at which we observe this transition, unlike in MPIfR. Therefore, it seems unlikely for this source that it is actually the accretion flow that is confining the jet, just because the two scales are really so much different. By considering also the VLA data, which we also had available, we have also studied how the expansion profile evolves on kiloparsec and megaparsec scales. And basically what we see is that this conical shape is preserved up to the end of the source. We only observe a slight steepening of the profile, but basically the jet collimation occurs only in the innermost regions, which are probed by the Millimeter-VLBI observations. So for this source, we propose that if the jet is confined actually by the external medium, which may not actually be the case, then this medium must be something that extends on much smaller scales. For instance, a thick hot disk, which is expected to exist in this source of the type of, for instance, the advection dominated accretion flows, which are expected to extend on a scale of the order of 10 to the 3 Schwarzschild radii. Now, as I said, in the past years, we have accumulated a lot of evidence also for other sources concerning the properties of the parabolic region. Therefore, we have decided in this work to also compare what we obtained for NGC315 with what it has been obtained with other sources in the literature. And therefore, we have considered a sample of 27 sources which, with redshift less than 0.15, which have a known jet shape at the base and a known black hole mass, so that we could be able to compare the jet expansion profile once they have been mass scaled. So the jet expansion profile in units of Shashi radii. In physical scales, these are different scales, but in units of Shashi radii, we should observe similar scales. So in this plot, I'm showing again the same width as a function of distance from the black hole for this time for different sources. And these sources here are the 14 sources in the sample which have show a parabolic shape at their base. And GC315 is this blue points here, which, as you see, it overlaps very, very well with the profile of M87, which is the magenta points. However, other sources like Cygnus A or 3C120 present wider jets at the same distance from the black hole. So while all these jets have similar expansion rates, at the same distance from the black hole, we observe different widths. So we think that this may be an indication that the initial width of these jets are not the same. So as I mentioned at the beginning, in M87, we have actually measured that the jet base is really, really narrow. And this fits with what we are seeing here. The jet starts really narrow and then expands parabolically. The jet of Cygnus A also expands parabolically, but at the same distance, we already have much wider jet width. And this indeed match with the fact that we measure a larger sides at the jet apex. So this may be an indication that this blunt for pain component, so the disk wind component in the jet, may not be as equally prominent in all sources. So we have tried to see if this, try to investigate if this, if there is a relation between this behavior and the classification of the sources when we look at the nuclear properties. So we have classified all of the radio galaxies in our sample as high excitation or low excitation sources by considering the X-ray luminosity. So by calculating the ratio between the X-ray luminosity and the Eddington luminosity, we have discriminated between low excitation and high excitation sources by assuming a dividing value of about 10 to the minus 3, which is what it has, which it follows the results of a previous paper, which basically have investigated the X-ray properties of sources classified based on the optical properties, which is the original characterization of low excitation and high excitation sources. And once we have done that, we have compared again these profiles, this time also including the BLX, but dividing the sources based on their class. So in blue, we have high excitation sources. Most of these are FR2s, but not all. And in magenta, we have the low excitation sources. All of them are FR1s. And in yellow, we have the BLX. Now, as you see, the BLX actually have a steeper profile. Indeed, the shape of most of the BLX in our sample is conical. Why is that? Because BLX are probed on larger scales on average, and therefore, if they were collimating, this has happened in the part that we do not resolve in BLX. So we probe them already in the conical shape. But still, you can see that the BLX align quite well with most of the FR1s, while all the high excitation galaxies lie on a higher, upshifted profile. So this, it seems possible that indeed high excitation sources, which are those powered by this classic thin disk, may have a broader wind with respect instead to the low excitation sources, which do not really have this thin accretion disk, they have this hot accretion flow, and in which if a jet sheet exists, it must extend for really, it must be anchored in the innermost regions of the accretion disk. So basically, for high excitation sources, there is a strong Blanford Payne component. For low excitation sources and BLX, there is mostly the black hole driven component, so the spine, and a narrow layer which may be launched by the innermost regions of the accretion disk. We have also studied the extent of the collimation region in these sources because many of them show actually this transition between parabolic and conical shape. And we have studied how this transition distance is distributed in high excitation and low excitation sources by expressing this distance both in units of parsecs and in units of Schwarzschild radii. So first of all, if you remember at the beginning, I've shown you the sketch saying that we believe that the collimation region occurs, is extended for about 10 to the 5 Schwarzschild radii. This is what we find for MIT7. But as you can see, the range of transition distances which we observe is actually much broader. So we have sources which collimate on a scale of 10 to the 3. We also have sources which collimate on a scale of 10 to the 7 Schwarzschild radii. In this left plot where we express the transition distance in units of parsecs, you can also see that the NGC315 is not the only source which shows a sub-parsec scale transition. There are two more sources which also belong to the low excitation class. And in general, powerful sources seem to collimate on larger scales. This becomes particularly evident when we express the transition distance in units of Schwarzschild radii, where we, with the exception of Cygnus A, we really have a separation between the two distributions. Of course, the numbers are still small and we don't have much statistics, but this is a first indication for a possible different behavior. And we will use our new data, which include many more Herg and Lerg sources, to enlarge this sample and actually test whether this is true. It is interesting that this result, that powerful sources collimate on larger scales, matches the results obtained recently by Potter and Cotter, which shows that the FSRQs, so the parent population of these powerful radio galaxies, accelerate over larger scales, typically larger than 10 to the 5 Schwarzschild radii, with respect to BLX. So this also confirms the fact that indeed acceleration and collimation happen on they are co-spatial, they happen on the same scales, but they extend, they have different extents depending on the properties of the disk. So in the end, what is that collimates jets? We still don't know, but what we have shown with this work is that sources which are powered by thin disk, they present more extended outer sheets, and they also collimate over a more extended region. For these sources, when we talk about ambient medium, we are probably referring to powerful disk winds which are launched by the outer regions of the accretion disk. So if the jet is collimated by the ambient medium, then probably it is disk winds that play the main role for the collimation of the central part of the jet in powerful sources. And interestingly, this matches the predictions by modeling of jet confinement by hydrodynamic wind layer, which show that indeed the more extended, the larger is the radius of the disk wind, the more extended is the acceleration region. On the other hand, for sources which are, for low luminosity sources like NGC315, this wind, if there is not that prominent, and the fact that we observe that the collimation is already completed on sub-parsec scale may indicate that if the jet is collimated by the ambient medium, this ambient medium is possibly the hot, thick disk which powers the jet. It is also interesting that, of course, this scenario of the collimation by these queens may have some important implications for the FR1 FR2 dichotomy. We don't know why the most powerful sources can keep such a high degree of stability for such long distances, but models show that actually in the presence of a prominent jet sheet, also the stability of the jet is increased because the outer sheet protects the inner spine by entrainment of stars, for instance, or of gas from the interstellar medium. So if this is actually true, then the presence of the jet sheet may contribute to the development of the FR1 dichotomy, because the jet manages to keep its stability without being disrupted within the galaxy. So this is my summary. So I would say that our first results on these observations are encouraging. We're going to have many more sources which are available for jet formation study. We have also found a really good candidate in addition to MIT7 for really probing the scales less than 10 to the 2 Shashi radii, and potentially this source NGC315 may also be a source which is suitable for observations with the Event Horizon Telescope. Well, the rest I have already talked about, so I will leave you with a summary, and I'm happy to have your questions.
Thank you very much, Bia, for this very, very interesting talk. Do we have any questions for Bia? You can either turn on your microphones or raise your hands. Nick?
Yes, I do have a question. Yeah, in the previous slide and in this one, that's okay. It's okay. Leave it at this one.
Okay.
And then if need arises, we go to leave it to the summary.
Mm-hmm.
Okay. So this you say that the hot inner flow collimates the jet. Isn't that what you said? Or
yeah, in the low luminosity objects, it may be this hot disk which
yes.
initially confines the jet.
Yeah, right. I cannot visualize how this can happen in the sense that the jet feeds from this hot flow, from this hot disk. So above and below this hot flow, a jet is forming. So how can this flow then collimate if it feeds the jet? In other words, the bottom of the jet is the top of this thick disk.
Well, not necessarily, because this hot accretion flow feeds the black hole, but in the innermost regions. But then it has a thickness which the jet already extends in a region where that is. So the disk feeds the jet in the innermost region, but then it has a certain thickness, and the jet expands in a region where it has a wall, which is formed by this thick disk.
So okay, now I visualize what you're saying, but then I do not understand why the inner part only of this thick disk emits a jet and not all of it.
Well, actually, models of advection-dominated accretion flows predict that also that there are actually winds also in the at larger radii actually. But when I say that the sheath is narrow, I'm talking about the part of the jet which we see in VLBI observation. So I'm talking about the strongly magnetized and collimated wall which surrounds the central spine. So there may be, there are probably outflows also at larger disk radii, but the sheet which I'm mentioning here is launched only in the innermost regions, and this is just because we measure it. I'm not saying that this is how it is. This is what we measure. So we measure that the jet apex is really narrow. So, and since we measure very low speeds also in MIT7, then this must not really be the spine. It must be still the outer wall, but an outer wall which doesn't really extend for much, for very, very extended radii.
If I continue, one more question, Vaso.
Please go ahead.
Okay, so if the magnetic field ejects the jet, why do you need a wall to collimate it? Why can't the magnetic field do it itself?
No, indeed, there are models that only in which the magnetic field is sufficient to provide the confinement, but they don't all agree on that. Other models predict that a confinement from the medium is anyway necessary to achieve the observed degree of collimation. So there is not a consensus on that. And that's why it is so important to get observational constraints.
Okay, thank you.
No problem.
Thank you. Any other questions for Bia?
Sorry, it went a bit long. I thought it would be shorter. Sorry.
It's fine, lengthwise. Questions for Bia?
Just one question.
Yeah, Nico?
Is this work published already?
Yes, yes. It's in press. It's about to be published in ANA. Yes.
Okay, okay. Thank you.
Anything else? Okay, if there aren't any more questions, let us all thank Bia very, very much for this very interesting, fresh out of the oven results.
Thank you.
And we will give you a rain check for an in-person visit once the COVID pandemic is over. We will be delighted to have you back. Thank you very, very much
for inviting me. See you soon.
Thank you. Bye, everybody.
Bye, bye.